In this video, we take another look at the Schwarzschild solution and black holes. We have already covered this topic in a previous video using the good old spherical coordinates. However, as we saw in that video, the spherical coordinates become problematic near the horizon of a black hole. For example, the light cones become infinitely thin, which makes it difficult to visualize the dynamics of test particles, including light, near the horizon. A helpful way to avoid this issue is to choose coordinates that preserve the 45-degree angles of light cones everywhere. Such new coordinates are not only helpful in studying a black hole, but also the dynamics of a gravitational collapse into a black hole, which is an essential ingredient in Hawking radiation. One such set of coordinates is called the critical secarish coordinates. 2m is the Schwarzschild radius in units where the gravitational constant and the speed of light are both 1. R and t are the radial and time coordinates that appear in the Schwarzschild metric. We will leave the solid angle term untouched. To see how the spacetime diagram for r and t relates to a spacetime diagram for u and v outside of the Schwarzschild radius, we first observe that v over u depends only on t. In other words, the relation between v and u is a straight line through the origin with a time-dependent slope. The second observation we can make is that the expression u squared minus v squared is a function that depends only on r, which is nothing but a hyperbola. We can do the same for the region inside the Schwarzschild radius. One important property of this coordinate system is that the light cones run 45 degrees to the u and v axis everywhere. To prove this, we need to compute the metric tensor. Adding the solid angle term, we recover the Schwarzschild metric on the right side, and on the left side, we get the metric in terms of u and v. If we follow the same steps for the inside of the Schwarzschild radius, we find that the metric is the same. Notice that the apparent singularity that plagued the Schwarzschild metric at the horizon has vanished. It appears neither in the coordinate transform nor in the new form of the metric. The only singularity in the metric is the actual physical singularity, the center of the black hole. Now that we have the metric, we can work out the geodesics of light rays moving in the UV plane. For that, we need only this part of the metric. We see immediately that the solutions to this equation are v equals u plus a constant and v equals minus u plus a constant. So indeed, the light moves diagonally everywhere in the UV spacetime diagram. Let's consider a light beam starting at some time in the past, moving towards the center of a black hole. As the t parameter increases and shoots off to infinity, the light beam crosses the horizon, after which point the time decreases from infinity to 0 and continues into the past as measured by t. It looks like the light beam is traveling back in time in this portion of the diagram. But is it really? As far as the beam is concerned, it is simply traveling through spacetime. Just because the coordinate labels say minus a number is irrelevant to the beam. This way of labeling spacetime coordinates is a convention that may be convenient to an observer far away from the black hole, but becomes nonsensical near and past the horizon. It would be like bringing a barometer to the moon for the purpose of measuring altitude. It works on Earth, but on the moon it would give a reading of either 0 or negative, depending on its calibration. Now let's look at two observers, say Donna and James, who start out at the same spacetime point somewhere in the past, but then follow different trajectories. James is hovering some distance above the horizon, while Donna is falling into the black hole. We don't really care if Donna is in a freefall or not, as long as she's moving towards the horizon. At some point, say here, Donna sends a signal to James, which he receives here. A bit later, Donna sends another signal, and then another. After some finite time, according to Donna's proper time, her signals have nowhere else to go but towards the singularity. They cannot reach James anymore. The only portion of Donna's world line James sees is this one. If the signal sent by Donna increased in frequency near the horizon, James would continue to see Donna approach the horizon. In particular, if she managed to increase the frequency at which she sends the signals at just the right amount so that they arrive at James at regular intervals, as measured by James's clock, he would see Donna approach the horizon but never cross it. If the signals carried interesting information, such as Donna undressing, James would see her undress more and more slowly with each signal he receives. Eventually, to James's disappointment, all he would see is a frozen image of her, reaching with one arm between her shoulder blades. Realistically, however, Donna would not be able to increase this frequency indefinitely due to technological limits, and James would eventually lose sight of her forever. It is a common misconception that because James sees Donna slow down, therefore Donna, if she were to receive signals from James, would see James spy on her super fast, and infinitely so as she crosses the horizon. But this is not the case. Let's say that James starts sending signals to Donna here. And continues to send signals. Donna, before she's destroyed by the singularity, would see what James was doing during this portion of his world line, which, as we can see, lasts a time that is comparable to the two observers. So Donna might see James speed up a little bit, but not by much. The critical secarish coordinates help us visualize Donna's trip across the horizon, but not so much James's. James goes off the chart into infinity where we can't follow. Wouldn't it be great if we could see James's location at all times using only a finite piece of paper, or in our case, a computer screen? To do this, we need to change our coordinates in such a way that infinite values of u and v will map onto finite values of some new variable u prime and v prime. Also, if we could do this while preserving the 45 degrees of the null geodesics, that would be even better. One choice of coordinates that accomplishes both is this, for both regions. To compute the differentials, we recall what the derivative of inverse tangent is. Then it follows that solving for du and dv, we get So indeed, the light cones are preserved. Now let's graph u' and v' as functions of r and t. The edges represent null geodesics at infinities and at the horizon. This one is called past null infinity and is denoted by this symbol. This is the future null infinity. Here is the horizon. And this line is sometimes referred to as anti-horizon because light can only move away from it, never towards it. These three vertices also have a name. This one is called past time-like infinity. It's where all spatial points converge at t minus infinity. This one is the future time-like infinity, where all spatial points converge at t plus infinity. And this one is the space-like infinity, at which all time points come together. And let's not forget about the singularity, which is represented by this purple line. This is called the Penrose diagram. It allows us to see the entire universe containing one black hole from the infinite past to the infinite future within a finite area. Of course, the coordinates become more and more dense as we move towards the edges. So to say that we see the entire universe is not exactly accurate. It can be useful for analyzing certain phenomena, such as the gravitational collapse, which will be the subject of the next video. Before we end this video, let's look at the trajectories of James and Donna on this diagram. They both start at an infinite past and then diverge. James moves towards the infinite future, while Donna crosses the horizon and moves towards the singularity. The picture looks very similar to the one we drew before, but now we can actually see their final destinations. As we will see in the next video, Penrose diagrams are not only useful for analyzing space-time in the presence of eternal black holes, that is, black holes that have always existed, but also the flat Minkowski space-time, as well as a mixture of the two.